So here we go on chapter 7, day 2. Yeah? No. The normal curve. We are in week 7, approaching the halfway mark. But here's where you're going to start with your groups. Should be an attainable task to work through that problem together, showing all the necessary components for a solution. So write down, as if this were an exam type scenario, how you would go about solving this. And then we'll go through a solution to make sure you're hitting on all the parts and pieces. You have everything that's necessary when we're going through it. So there you go. On your marks, get set, go. Was there. This is all it says. You go, x is approximately normal. So you started by drawing a normal curve. I mean, there was no question yet, but this is the start with reading it and then say, okay, what do I know? I know that this is a normal curve centered at 4. I do 1, 2, 3 ticks to the right, 1, 2, 3 ticks to the left. I mean, officially there's arrows on the ends of these. This is x because it says that this is x. So make sure I label my axis with what we're talking about. So my variable is x, I label it with an x. And then the first tick over will be 5.2, then 6.4. You don't have to label all of them. Just a couple so that I know that you know that each of those represents one standard deviation. It would be good to also do this. X follows a normal distribution with a mean of 4 and a standard deviation of 1.2. So having that nugget of information in addition, so there's not even a problem established as of yet. And you started with that. And so again, what I wanted you to start with that first slide is just, you saw information, you should have instinctually drawn a picture. Because it said, so before the question, we get a question. So now, with your groups, see if you can solve that equation, or that question. I'll redo the graph here.
I like to do it where it's like 4 minus 3.5. You know what?
So again, the given information, it's normal curve, which we already have a picture of. We have that normal curve drawn, centered at 4. 1.2 is my standard deviation, so 3 going out to the left and to the right. I'm going to label my points 3.5 and 4.25. 3.5 is there, 4.25 is about there. It can be close enough. I mean, if you know it's between the mean and one standard deviation, so anywhere in there would have been fine. It's not that picky for scaling, all right? If this were just a calculus-based class, at this point, then we would go and find the antiderivative of the equation, which we're not going to do. We don't have to do because the love of statistics is the fact that we know that every normal curve of any type, of any data type, that gets put through the standardization formula. You might be saying, what is the standardization formula? Z equals statistic minus parameter divided by the standard deviation of the statistic. So for this case, my statistic is whatever I'm taking, which is X, picking one person out of the population, minus the parameter. In this case, we're going to compare it to the mean, divided by the standard deviation of X, which we were told is 1.2. I can then find the standardization of both of those values. So I'm going to have Z equals 3.5 minus 4 over 1.2. And someone who already calculated that can tell me what that number is? Negative point what? 417. And then Z equals the upper value, 4.25 minus 4 divided by 1.2. And what was that Z score? 0.208. Thank you. All right, 0.208. As far as what are the minimum requirements for a problem, so far I've not drawn or done anything that's extra. So when we're doing this, you've got a normal curve drawn, you've got the shaded areas, you've got the boundaries of the shaded areas labeled and then shaded for what you're looking for between 3.5 to 4.25. You've shown the z-score formula. Then you show the z-score formula with numbers in it, and then find those values of the z. And if I wanted to, I could draw another axis down here and label it z. You wouldn't have to, but that z-score there is negative 0.417. This z-score here was positive 0.208. After this point, then it's a matter of going to that online tool that you have. And it depends on which way you choose to shade. You shade to the left or to the right. Will depend on how we do it. My preference, only because this is what just works for my head, is I'm like, well, I can either do like a greater than or I can do a less than. I like to find the tails. So I like to find what's less than 3.5. So that'll be less than negative 0.417. And did anybody find that area on their online tool? So this is the probability that z is less than negative 0.417. Did anybody find that area? 0.3384. Is that what you said? Yep, so that's this area. And then this would be the probability that z is greater than, it's not a very good greater than sign, greater than 0.208. And that would be this area. And did anybody find that area? 0.417. Okay. Now, is this intentional? Sometimes the answer is yes. Because you're going to look and say, well, this is 0.417. That z was negative 0.417. You just have to be careful when we're doing this. This was a z-score. This is an area. We're going to be dealing in a lot of decimals and values and things along those lines. And you really want to keep track of what's going on. My advantage here is I have different colors to try to keep it all separated out. My z-scores were in yellow. Areas, I started to write areas in green of what I don't want. And then the green or the area I do want is the yellow, which corresponds to this here. And then your last step would be to figure out that calculation. The probability that, 3.5 less than x less than 4.25. And if I can, I'll just go ahead and move everything up there a little bit, is equal to 1 minus 0.3384, because the whole area under the whole curve is 1. I'll subtract away something I don't want, and then I'll subtract away the other thing that I don't want, which is 0.417. Are there other ways you could have used the technology tool to get there? Yes. As long as you're showing how you're getting there, I'm fine with it. But I can't just have an answer. Got to show process. And what is that number? 0.224? 244? 0.244? Is that what you said? Yeah. Okay. Do I have anybody to bobblehead and confirm that? All right, got some bobbleheads out there confirming that is the answer. All right, so when you're talking about answer, this is an answer. That's the probability. And if you wanted to, you could say there's a 24.4% chance. Let's see, there is a 24.4% chance an individual will have, and then I got to remember what the context of the question was. Will take between 3.5 and 4.25 hours. All right, so there I've taken my answer. I've linked it back with context into what the question was asking. I have my units included. Oftentimes, it's a restatement of the stem of the question with what your solution is. All right. And at this point, would you say that something happening 24.4% of the time, is that uncommon? Yeah, not really. It happens a quarter of the time. That's pretty common. We're going to start getting into this idea of, well, how much would be too much? You know, if something only happens 5% of the time, is that uncommon? 2% of the time? 1% of the time? When does it move from, that seems big or too small, to, wow, that shouldn't have happened. That is way too big or way too small. And we'll actually define some values that will say, hey, if it's more than this or less than this, we'll consider it to be too far away from the mean to have happened just by chance. Second question. It's different than the last. Take a moment. Similar idea, but your equation will change a little bit. But let's go ahead and I'll draw a picture as you're drawing a picture, and then go ahead and work with your group. Quick and efficient. There's one big difference. Because it says the mean. And I intentionally left that off because it's not 1.2 anymore. Because it's no longer a distribution, it's now a sampling distribution. Because it said the possibility that the mean of a month's review. So it's not a single value anymore. Now it's the mean of whatever this group is. Group of 16, oh, it's 16, so that shouldn't be 12. That should be 16. So 1.2 divided by the square root of 16, well, that's 1.2 divided by 4, so it's going to be 0.3. So this right here is 4.3. This one here is 4.6. This here is 3.7. This is 3.3. If I can subtract well, 4. So it's not a single value, it's multiple values. We took the average of them, so now I'm dealing with a sampling distribution, much like we did with the cell phone contacts. Instead of a single cell phone contact, we did samples of size 3, and then of size 5, and then of size larger, and then realizing that since my original distribution is normal, my sampling distribution is normal. I write it down because that is very important. Very important to know and very important to be able to communicate. .5, 4.25. Move some of that up. So in the past, what we did, we said the statistic was I'm just pulling a value, so I was pulling an x. This is not pulling a value, it's actually pulling an average. So instead of an x, it's now an x bar. We're still comparing that to the mean, and the reason why is because the mean of x bar and the mean of x are the same value. So I could say it's either the mean of x or the mean of x bar, but they're the same number. The average of all the averages will equal the average of the original distribution, divided by the standard deviation of the statistic. Now it's the standard deviation of x bars, so it'll be sigma over the square root of n. Z equals 3.4 minus, not 3.4, 3.5 minus 4 divided by 1.2 over the square root of 16, which I already said as we looked at that, that's 0.3. Now, of course, I did that math in my head. You should always check me with math in my head. Square roots, I'm good. Dividing, I'm usually good. Subtraction, I'm terrible. I am just horrible at subtracting. All right, so this will be 0.5 over 0.3, negative 0.5, which will be a z-score of what? Negative 1 point. How much? 1.66 repeating? And then I would go to online tool. So if you've already got it up and running, grab that online tool. And this is where it depends on what you like to do. I am usually looking out here at this one. So this would be the probability that x bar is less than negative 1.667. So here, the probability that X bar, or no, sorry, X bar, Z. Wow, I got to make sure I'm not mixing and matching. We converted it to Z, so I got to make sure that that's a Z. Z is less than. Down here, this is the probability that X bar is less than 3.5. It's the same value. And I'm talking and pausing so that you can be, calculating that for me and then shouting out a number. What is that number? 0.0477. This is that area. 0.0477 or 4.77% chance. And then this area is the probability that Z is greater than, now I got to find the other Z value. Z equals 4.25 minus 4 over 0.3, which is 0.25 over 0.3, which is point how much? 833 repeating. And then we go to the area. So this would be 0.33 repeating, or 833. And what is that area? How much? 0.20233. Now again, anytime someone in this classroom is shouting out a number, there better be at least a few more of you verifying this on your own, or we're all getting the wrong answers. All right, good. It also is verifying that you know how to use that online tool, so you're not trying to figure out on the day of exam, like, well, I saw them do it once. I think I know what I'm doing. Don't ever go with that. Know that you know. Don't think that you know. And then the process remains the same. I don't want this area, because that's the tail area. I don't want this area. That's that tail area. So the probability that 3.5 less than or equal to, actually just going to be less than, doesn't matter, X bar less than 4.25 is equal to, and someone has done this subtraction for us, 1 minus those two numbers, 74.99%, or 0.7499. And then I would write a sentence, which I leave you to do right now in the next minute maybe, before we go to the next one, where you write a sentence that basically says, there will be a 74.99% chance that the average time it takes to complete a month's reviews will be between 3.5 and 4.25 hours. Now some of you are going to say, could you repeat that? And the answer is, it is on video. Go back and watch it. You can listen to it as many times as you want. Yes, you don't need to take a picture. It's online. Yeah, the videos are online every day by the end of the day usually. Linked on the Check Your Understanding page. All right, next thing is up. This one is 2 questions. They're different questions. So as you read the question and you see the difference in the question, identify. What's the difference? Why are there 2 different questions? What's one? What's the other one? This would be the go ahead and shout it out if you see the difference.
One's asking for the average of averages, one's asking for just the normal.
Yep, so this is asking for one review. This says for the mean review time. So 1 review versus the mean review. So when we're doing this, as you're thinking, and hopefully we're going to get you to a place where you're automatically coming up with these thoughts, the standard deviation, I don't like blue, we'll go to yellow. The standard deviation of this one is the standard deviation of x, which is 1.2. For the mean times, it will be the standard deviation of x bar, which will be 0.3, only because I already calculated it out before, as sigma over the square root of n. The mean of this one will be 4. The mean of this one, that's the mean of x's. The mean of x bars will also be 4 hours. And then, draw a picture. That's a bad one. I'm going to try to get a little bit better at this. Slow myself down. There, 4, 1, 2, 3, 1, 2, 3. That's 5.2. But it's asking for the 95th percentile, which is some value right up there. This area to the right is 0.05. The area to the left is 0.95. Because the 95th percentile is the value at which 95% of the data is at or below u. We've got this, so then I'm going to use my z-score formula, which is z equals x minus mu over sigma. What do I know? I know x. Oh, no, I don't know x. I know mu. I know sigma. I can find a z-score using technology. So here's where you grab that technology tool. You're on the same applet that you were before. And in that applet, you're either in the red box, going to put 0.05 if you're doing above. So if your applet is set to show the area above, you put in 0.05. If you have the applet to set to less than or equal to, you plug in 0.95. And if you put in that value in the red, it will tell you the corresponding z-score to the left. And what is that corresponding z-score? 1.645? Should be something like that. What does the computer say? 1.64485? 1.64485. And then my unknown is, what is that value? That's what the question asks. Find the 95th percentile for time to complete. Well, that's the z-score for it. There's the average and the standard deviation. I can algebra that thing and find x. I hope you can too, because I'm going to move to the next half of this question. Next half of the question says I have a normal curve again, because the original curve was normal, so that means that was not a very good drawing again. Better. 4, 1, 2, 3, 1, 2, 3. This is 4.3, 4.6, because these are for x bars, because it's the mean time. That area is 0.05, this is 0.95. Z equals x minus mu over sigma over root n. 95th percentile, still with a z-score. We already figured out the z value for it, so that'll be the same. X minus 4, but now it's going to be over 0.3 instead of over 1.2. And then you hopefully can algebra that thing and find the x value. Which one will be larger? Second one or first one? And then the question would be, why does that make sense? As you sample more and more, variability decreases, because I'm taking an average. All right, so to have an average value, it becomes harder to have a larger value, an average value above the mean. You'd have to have some extreme values to get a really large value of an average above the mean. Whereas you could pick an individual and you could very easily be a couple points away. In this case, even to get to 4.5, that's a long ways higher. Right? You're a couple standard deviations out as opposed to within one standard deviation of the original data plot. So it's easier to have a single value that's high or low. It gets harder to have an average that's high or low because when you average it, you're taking out the extremeness, for lack of a better word. So that was review. That's stuff that we've done. You've been working on the problems out of your book related to that. Again, ideally, it should have been something like, yeah, okay, I've been doing these. I've been practicing these. I've been working on these. If you haven't, you need to. Central limit theorem for sums. I introduced this last time we met. I said it was the second half, and it was a little bit lesser. It's just not as common to be used, but it is technically a part of the central limit theorem, which says that if we have a sample of size n that's large, and n is large enough, and we sample some data points, and those points are added together, the resulting histogram of sums will have an approximate normal curve. And then these would be the formulas, slightly different than how your book writes it, just because I'm different than your book and your authors of your textbook. All right. The average of the sums of the x's. All right. So if you sample 5 of them and you add them up, it would be the average of the sums. Well, the average of the sums will be equal to the average times however many I took. So if an average is 5, if we know the average of some data set is 5, and I select 10 data points, I would expect the average of those sums to be 10 times 5, or 50. So that would be the height, or the sum total of whatever those 5 are that I select. The standard deviation, that should be a square root. That didn't come through on. There's some things that don't pop through when I'm copying and pasting from one program to the other. Give me 1 second. Be a square root down there as well. So not sure why. I'm going Mac program to Mac program, but some things aren't copying over. So this standard deviation will be, instead of being the standard deviation divided by the square root of n, for sums it's standard deviation times the square root of n. This stays the same. Instead of x, it's the sum of x's. Or instead of x bar, it's the sum of x's. N times, so the mean of all the sums, and then the standard deviations of the sums. Right, so there's that general worded phrase that's on the formula chart that we'll have for all tests and quizzes, tests, really, exams, that you have access to. In words, that's what it is, and then all these different scenarios come up that require us to then have slight modification to what's going on. So an unknown distribution has a mean of 80 and a standard deviation of 12. This is important. That'll mean something. So the mean was 80. The standard deviation of that was 12. So I'm going to write those two things down. One thing I did not do is I did not draw a normal curve because it says the population is unknown, which means I don't know the shape of it. I don't know anything about it. I just know the average and standard deviation, which is kind of weird. Won't often happen in the real world that you'll know the average and the standard deviation without knowing the shape of the distribution. But for argument's sake right now, we don't know what that is. It says find the probability that the sum of the 95 values is greater than, so I want to find the probability that the sum of my x's is greater than 7,650. All right. N is 95. Since n is 95, that's not a 95, is 95 and is greater than 30. the central limit theorem proves that the distribution of sum of x's is approximately normal. To do what I'm going to do next without making that statement is bad math. You have to link the reader along so that they know, and the reader being me, your professor, that they know that you know what you're talking about. How did you know that you were allowed to draw a normal curve? I too often hear people say, because it's normal. I'm like, okay, what is it? The distribution is not normal because it says it's an unknown distribution. But the moment I have a sample size over 30, that's the amazing aspect of the central limit theorem. That means now the sum of the x's will follow a normal distribution. So then I can draw a normal curve. And my variable here is the sum of my x's. It's not x. It's not the average of the x's. It's the sums of the x's. And my mean, when I'm doing sums of x's, that's where that formula set was. The mean of the sum of x's is equal to the n times the mean of 1x. All right, the mean of 1x is 80. So the mean of 95 of them is going to be 95 times 80, which I didn't do in my head ahead of time to memorize that number. A little bit louder. 7600. All right. The standard deviation of the sum of x's will equal to the square root of n times the standard deviation of x. That was the formula from that last page. So now you're going to take 12, which is the standard deviation, times the square root of 95. And I will say the sum of x's approximates a normal curve with a 7600 mean and a standard deviation of, one more time, 116.96. Any bobbleheads in the room approve of that number? Yes, excellent. I'm going to go 1, 2, 3. So this will be 7716.96. And that's all I'm going to add for now. My boundary point is 7650, which is somewhere here. I want greater than, so I'm going to go this way. Fill that in. Shade this zone. The probability that the sum of the x's is greater than 7650. That's what I'm looking for. I need a z-score formula. Ooh, undo that. Select everything and then move it all up. Z equals stat minus parameter divided by the standard deviation of a statistic. My stat is the sum of x's minus the mean of the sum of x's divided by the standard deviation of the sum of x's, which will be 7650 minus 7600 divided by 116.96. For a grand total of .43044 are numbers I'm hearing. All right. There we go. Then we go to the tech tool. Go online applets, normal distribution, a z-score of 4.43044. All right. Now when we're doing it, because I drew my picture up here, just a quick refresher, that was 7716, 7600. So I know my z-score is not going to be over 1. It's going to be somewhere between 0 and 1. Because the first standard deviation over is 7700, so 7650 is somewhere in that first one. So I know my z-score was going to be somewhere in that range. Again, these are just like little mental checks you can do as you're working through these problems. And then I go to that distribution, and I find that the area, the probability that the sum of x's is greater than 7650 is equal to 0.33344. Now, if you were an individual who used to love rounding and you rounded this somehow, you're going to get a slightly different answer. And I've said it once, I'll say it again, don't round. All right. I mean, maybe when I'm done, I say there's a 33.34% chance, but I'm never going to, and I recommend you not, have anything less than 4 decimal places. All right. So if I would have taken this and just lopped it off there, you can either round or truncate. You could use up to, but I would never go less than 4 decimal places. What happens is you start to lose data at that point. So I don't know why I changed this. From sample size of 90. So let's just assume that was supposed to be 95. Go ahead and try to work through this one quickly with your group that you're with. Procedurally, very similar to what we did, but show everything. Show everything. And marks its echo. So again, procedurally, identifying that I know that the sums of the x's distribution is normal because of the central limit theorem. I forgot to cite that. Because CLT. All right. Since n is greater than 30, comma, the sum of x's approximates a normal distribution with a mean of this and standard deviation of that. Due to the central limit theorem. I could start with, because of the central limit theorem, and then go that way. Show my formula, values into it. Here's my z-score. I go online and basically, now I don't know what your online tool goes, but I know that it's really unlikely you're going to be more than, well, much more than 3 standard deviations below. But 5 standard deviations below is incredibly, incredibly rare. All right. Being able to find the 33rd percentile will be procedurally like how we did earlier. It's just using different formulas for the sums. And then this one is you can't do it. Don't be shocked if your book, or me, but not often me, throws something tricky at you like this. An individual from the population is drawn. After you've done the previous ones, you're in the habit of writing normal curves and saying because of the central limit theorem, but this is an individual from an unknown distribution. And we know nothing about this distribution for how it is shaped or anything like that. So in this case, you cannot find that probability.
So if we were given that on the test, we would say we cannot find the probability.
Because we do not know the shape of the original distribution, and this is just one individual, this problem cannot be solved. Yeah. And then the really paranoid people in the classroom would say, but if it's normal, this is how we would do it. And then they would work through it. I mean, not wrong to say, but if it is, and then you run a hypothetical, but you're taking a lot of time to not do something that you're asked to do. The assessment in this would be, can you determine that actually we don't know we can't do anything with this? There's so much data that exists out there in the world that people do samples of, and then they try to make conjecture on that they can't do because it came from an unknown distribution. Like, oh, we're just going to assume it's normal. That's a pretty broad stroking assumption, unless you know something that I don't know. All right? Some people like to think things like income distribution is normal. It's not. Income distribution is always right skewed. You're going to have a lot of people making some and a few people making a lot everywhere you go. So, I reminded you, next class, we are in LR 102.